Okay, let's continue to talk about these three potentials, and particularly the action potential. But the three potentials were the resting membrane potential, and of course that's caused by leak channels, both sodium and potassium leak channels, more potassium leak channels. And since potassium's leaking out all over the cell, and we can measure the voltage inside the cell, but since it's so much potassium's leaking out, then it's going to be a very negative number. It would be more negative, but fortunately we have some sodium leaking in, but much more potassium leaking out due to the number of potassium channels, leak channels. So resting membrane potential found everywhere in the cell, our leak channels found everywhere in the cell. Okay, our next potential was actually called the synaptic or graded potential. And the synaptic or graded potential is this section of the graph here. It's what's causing us to either reach threshold or keep us from reaching threshold, and that's caused by the chemically gated channels. Here's a chemically gated channel. Here's the chemical, the neurotransmitter, which could be many different things, and of course what the chemical does, it opens up the chemically gated channel to allow our ion to flow through. In this case, it's opening up and allowing sodium to flow into the cell. Therefore, that would be an excitatory situation, because if positive ions move towards the cell, then what's going to happen is my voltage is going to increase towards threshold. Now keep in mind, we not only can have excitatory situations, we can also have inhibitory situations. So again, even looking at this, notice I have an excitatory synapse, meaning that at this point here, I am opening up channels that are allowing positive ions to leak in, which is causing my voltage to rise. But here I have an inhibitory synapse. So that means one of two things. Either I'm opening up channels that allow negative ions to flow in. A good example of that is GABA, opening up chloride channels to allow chloride ions, which are negative, to come in, which is going to cause my voltage to drop, because if something negative comes in, it causes this to drop. The other option for that is if I open up a channel that allows positive ions to not go into the cell, but to leave the cell. Okay, and so anything that causes my voltage to drop below resting membrane potential is called hyperpolarization, but the signal doing that would be an inhibitory signal at an inhibitory synapse. But either way, if I'm not at resting and I haven't reached threshold, then I am somewhere in the graded potential, the synaptic potential. It's called synaptic because it happens at a synapse. It's called a graded potential because it can be different amounts. It's never exactly the same, or it doesn't have to be exactly the same. So for instance, if I get a bunch of positive ions flowing in, then I'm going to go in this direction. If I get a bunch of negative ions flowing in, I can go in that direction. But in reality, what happens is I usually get a combination of both excitatory and inhibitory. So then I have to integrate, I have to sum up whatever's going on and see if my integration makes my voltage reach or not reach threshold. In this case, neither my excitatory signal or my integration has reached threshold. Therefore, if that was all that was happening in this cell, then I would not be sending an action potential. Again, here's a good example of what's going on at the synaptic potential at the synapse. Here, this is the axon bulb of one neuron synapsing with the postsynaptic membrane of another neuron. The postsynaptic membrane being kind of like what we talked about the motor end plate of the neuromuscular junction being. Here I've actually got my specialized receptors that are chemically gated channels. And again, they're receptors, they're chemically gated because the neurotransmitter will be the chemical that causes them to open. In this case, it would be direct and not indirect. But anyway, because direct, it opens up that direct channel, allowing the sodium to rush in. If it were indirect, the chemical would attach here, but it would then serve as a cascade of events before we opened up an ion channel somewhere else in the membrane. Okay, but anyway, this is what's going on in the synaptic potential here, where I'm releasing my neurotransmitters at either my dendrites or my nerve cell body. Again, in this picture, we see that there's a lot of synapses going on even at the nerve cell body. So again, notice that we are at a synapse. We have our chemically gated channels. So they're responsible for our synaptic or graded potentials. Again, the graded potential means that it can vary in its intensity. It can vary. This is a graded potential. That's a graded potential. This happens to be an excitatory signal for the graded potential. This happens to be an inhibitory signal for the graded potential. And of course, what we do is we sum up both of those to see what the sum of both of them, which is called integration, would be. And if it doesn't reach threshold, then we will not send the action potential. But if it does reach threshold, we will send the action potential. Okay, here we see our leak channels, and notice we have potassium leaking out of the cell and sodium leaking into the cell. Okay, so our sodium-potassium pumps then will eventually restore the balance so we don't reach equilibrium on both sides. But since we have more potassium out, not because more goes out through the single channel, but because I have multiple channels throughout the whole membrane, then sodium leaking out is going to help, along with the proteins that are negatively charged, it's going to help this inside of the cell during a resting membrane potential. We can measure it around -65 or -70, so that's why it's negative, because we got positive ions leaking out and we have negative ions that are too big to leak out. Okay, now that would actually go down even further, except for the fact that we do have some sodium leak channels which are allowing sodium to come in. At the same time, we also have to recognize, now here's our polarized condition of our positive charge outside the cell and our negative charge inside of the membrane. Okay, so in each individual channel, however, because with the electrochemical gradient, in other words, we literally have more sodium being able to leak in than potassium leaking out per channel, because sodium has two forces acting on it. It actually has the higher concentration or diffusion, which is the chemical gradient portion, and it has the electrical gradient, this negative charge, also attracting it inside. Whereas potassium in an individual channel, not as much potassium leaves as sodium comes in an individual channel, because it has the chemical gradient of potassium pushing the potassium ions out, but it also has this negative charge that's basically attracting the positive ions inside the membrane, not outside the membrane. So it has one force pushing it out, one force opposing it. It still has enough of the chemical gradient to make sure that we are pushing it out and not keeping it inside, but this is lowering the amount that can go out per individual channel. We make up for that, though, by having multiple channels all over the cell and fewer sodium leak channels, but multiple potassium leak channels. And that's what gives us this resting membrane potential. Okay, along with the leak channels that we saw here, because they are always open and our ions can leak across them, our other types of channels we've been mentioning are our chemically gated channels, where it literally takes a chemical like acetylcholine to bind to the keyhole and open them up before the ion can come in. Of course, that's what's going to happen in our graded or synaptic potential, because these would only occur where we have a synapse. Then our voltage gated channels, which takes a voltage, and the voltage that opens up this gate here is actually called threshold. So notice that once we reach a certain voltage, here they're indicating it's around minus 55 millivolts, then that gate opens up. Now our ions can go through. But one thing that happens in sodium channels is they not only have an activation gate, which is basically opened up by the voltage, it also has an inactivation gate that is a timed gate. It closes after a certain amount of time. So even though the voltage can be reached to allow the ions to go in, after a very short amount of time, this inactivation gate closes, which prevents more sodium from coming in, even though this gate may still be open. Now, the other gate that we're not going to really talk about as far as the action potentials, but I just want to introduce to you, is the mechanically gated channel. And this is where a mechanical pressure actually opens the gate and allows the ions to move through. So again, a lot of times touch and injuries and stuff have this mechanically gated type channel in how they work and allow the action potentials to work. Again, our third potential, the action potential, which is literally what we call the nerve impulse, and it gives the exact same amplitude and duration signal everywhere it occurs, and it always occurs where our voltage gated channels are opening and closing. Now notice here's their axon here, and notice that here's our amplitude and our duration, and if we bring that over here, it's the same graph we were looking at. And what that means then, and this is kind of a very simplistic view, because in reality these green channels, which are the sodium channels, in reality they look like they actually look like this. They have an activation gate and an inactivation gate, and it's the voltage that opens up the activation gate. So in this simplified picture of it, what we see is that the voltage has opened up this, and if it's moving internal this way, then the voltage gate would open up first, and then the inactivation gate would finally close and keep more sodium from going in. Now, again, what is it that opens up that gate to begin with? Well, it's reaching threshold. It's when our voltage inside reaches threshold. Where am I going to find the first voltage gates? Well, I'm going to find them at the what's called the initial segment of the axon hillock, where the axon attaches to the nerve cell body. Now, notice that when this gate opens up and allows sodium to come in, then it triggers the next gate to open up, allowing sodium to come in, causes the next gate to open up, causing sodium to come in, okay? And then, as you see, this direction of the impulse means that we keep opening up those sodium gates, and here, because sodium depolarizes this, we see that it goes from being negative to positive as sodium rushes in. But shortly after sodium rushes in, then our inactivation gate closes. Here we see the inactivation gate close, okay, at about the time we reach about positive 40. So looking at our graph, at about the time we're reaching about positive 40, then those inactivation gates are closing, shutting off more flow of the sodium inside. But our potassium gates, and here our potassium gates are closed, that at about that point our potassium gates open, and then potassium starts leaving the cell, and when potassium leaves the cell, we call that repolarization. So you can see in our graph, here's repolarization, potassium leaving, here's potassium leaving, and again, that happens in an extremely short amount of time. If more potassium leaves to the point where our voltage drops below our resting potential, again, we call that hyperpolarization.